you're going to get an astrophysicist's explanation of the literal three-body problem. The intricate interactions of celestial bodies have long captivated the human imagination. Visuals of two suns on the horizon of Tatooine in George Lucas' iconic film, A New Hope, may not have been more than mere aesthetic instruments, but such complex celestial arrangements concerning 2, 3, or even more bodies have indeed long confounded rational minds. How can such objects, each with their own masses and gravitational fields, behave sustainably? The two-body and three-body problems challenge our understanding of predictability and chaos in the universe. So, will the world as we know it come to an end due to all of this chaos? Well, Neil deGrasse Tyson has clarified this three-body problem in the best way possible and shown us why it is not what we think. Let's get started. The three-body problem on Netflix. Before we dive any deeper into the core of the subject, let's take a look at the Netflix show of the same name that popularized the concept. Based on the acclaimed Chinese science fiction trilogy written by Liu Cixin, the series explores the consequences of humanity's discovery of an advanced alien civilization and the ensuing interactions between the two species. Among other things, the series also delves into the three-body problem and chaos theory. The show revolves around the discovery of a distant planet, Trisolaris, located in a three-star system. The planet's erratic orbit and unstable environment pose significant challenges for its inhabitants, who seek refuge on Earth by initiating contact with humans. As the story unfolds, the characters grapple with the complexities of the three-body problem both in a literal sense concerning celestial mechanics and metaphorically as they confront the uncertainties of their world and the universe at large. The series shows us why the three-body problem is chaotic and why it is difficult to predict the long-term behavior of complex systems. The interactions between the three stars in the Trisolaran system result in unpredictable outcomes, echoing the challenges faced by scientists in understanding similar phenomena in our own solar system. For instance, the interactions between Jupiter, Saturn, and other gas giants can influence the orbits of smaller bodies such as asteroids and comets, leading to unpredictable trajectories and potential collisions with planets or moons. Similarly, the gravitational interactions between the Earth, Moon, and Sun create tidal forces and perturbations that affect the Earth's rotation and climate patterns. Does this mean that chaos is brewing up in our own galaxy as well? Will the world as we know it end abruptly? To better understand things, let's explore the problem step by step. Introduction to the two-body problem. Before we explore how three celestial bodies can interact rather chaotically and unpredictably, let's get the basics straight. In a classic two-body problem scenario, the motion of two massive objects is predicted. This problem simplifies the dynamics by assuming that the two objects interact solely with each other. Let's take the Earth and the Moon for example, while temporarily ignoring any external influences. The gravitational interaction between two celestial bodies, often referred to as the Kepler problem in astronomy, arises in various astronomical contexts, including the prediction of orbits or escape trajectories for satellites, planets, and stars. Despite its apparent simplicity, the two-body problem provides valuable insights and accurate predictions when modeling celestial dynamics. A variant of the two-body problem, known as the central force problem, treats one object as stationary while the other experiences a force emanating from the stationary one. This model proves particularly useful when one object significantly outweighs the other, such as a light planet orbiting a massive star. In such cases, the heavier object's negligible motion allows for simplified calculations. The Earth-Moon system. The Earth-Moon system is a dynamic celestial relationship where the Earth and its natural satellite, the Moon, interact gravitationally. This interaction results in several observable phenomena, including the Moon's orbit around the Earth and the tides on Earth's surface. In the case of the Earth-Moon system, this problem simplifies the dynamics by focusing solely on the gravitational attraction between the Earth and the Moon, ignoring any other celestial bodies. The principles of gravity and mechanics, famously described by Isaac Newton in his work Philosophiae Naturalis Principia Mathematica, or the mathematical principles of natural philosophy, provide the foundational framework for understanding the motion of celestial bodies, including the Earth and the Moon. Newton's laws dictate that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. In simpler terms, the bigger the objects, the greater the pull between them, and this attractive force gets weaker as one of the masses moves away from the other. This gravitational force governs the Earth-Moon system, determining the trajectory of the Moon's orbit around the Earth. By applying Newton's laws and the principles of mechanics, scientists and astronomers can accurately predict the motion of the Moon relative to the Earth over time. This understanding not only helps in predicting eclipses and tides, but also plays a crucial role in space missions and satellite placements. Chaos in the three-body problem. Now, when we add a third body to this dynamic, the system's complexity increases dramatically. The three-body problem considers the gravitational interactions between three celestial bodies, each influencing the other's motions. Unlike the two-body problem, the three-body problem does not have a general analytical solution, making it much more challenging to predict the precise long-term behavior of the system. The chaos in the three-body problem arises from the sensitivity of the system to initial conditions. Even a slight change in the starting positions, velocities, or masses of the bodies can lead to vastly different outcomes. This sensitivity is a hallmark of chaotic systems, where predictability is limited and long-term behavior becomes nearly impossible to determine accurately. Real-world implications. Understanding the three-body problem has significant implications for various fields, including astronomy, astrophysics, and space exploration. For instance, predicting the orbits of moons, planets, and stars in multi-body systems requires accounting for the complex gravitational interactions described by the three-body problem. Moreover, studying such systems helps scientists comprehend the stability and evolution of planetary systems, including our own solar system. In conclusion, while the three-body problem introduces a level of chaos and unpredictability in celestial mechanics, it also offers profound insights into the nature of gravitational interactions and the behavior of complex systems. Through the lens of popular media like Netflix's The Three-Body Problem series, the fascinating and intricate dance of celestial bodies continues to capture our imagination, reminding us of the vast and wondrous complexities of the universe. Understanding the intricate dynamics of celestial bodies not only explains phenomena like lunar phases and eclipses, but also has practical applications in fields such as astronomy, navigation, and space exploration. The center of mass of the Earth-Moon system is located approximately 1,700 kilometers, about 1,060 miles, beneath the Earth's surface along the line connecting the centers of the Earth and the Moon. This point is closer to the Earth's center due to its significantly larger mass. The Moon orbits around this center of mass in an elliptical path, which can be predicted using Newton's laws of motion and universal gravitation. Historically, predictions of lunar phases and eclipses have been accurate for centuries. For instance, the ancient Babylonians and Greeks successfully predicted lunar eclipses using early observations and calculations. Modern space missions, like NASA's Apollo program, relied on precise predictions of the Moon's orbit to ensure successful lunar landings. Another example of a two-body problem is the Earth-Sun system, another fundamental celestial relationship in classical mechanics. In this scenario, the Earth orbits the Sun under the influence of gravity, while the Sun remains nearly stationary due to its much larger mass. Similar to the Earth-Moon system, the Earth-Sun system is simplified to a two-body problem, ignoring the influence of other celestial bodies such as the Moon. This simplification allows scientists to focus on the primary gravitational interaction between the Earth and the Sun. In this scenario, the center of mass is located inside the Sun, very close to its center due to the Sun's overwhelming mass compared to the Earth. The Earth orbits the Sun in an elliptical path. Johannes Kepler's laws of planetary motion, derived from observational data, describe these orbits accurately. Predictions of the Earth's orbit around the Sun have enabled the creation of accurate calendars and the prediction of seasonal changes. For example, the Gregorian calendar, introduced in 1582, was refined based on a better understanding of the Earth's orbit to correct the drift of the calendar with respect to the equinoxes and solstices. However, Newton's exploration of celestial mechanics revealed additional complexities within the solar system, particularly regarding the influence of Jupiter. Despite being much farther from Earth than the Sun, Jupiter's immense mass exerts a gravitational tug on the Earth as it orbits the Sun. This brings us to the three-body problem. Newton recognized the potential for instability within the solar system due to Jupiter's gravitational influence. Jupiter, being the largest planet in our solar system, has a significant gravitational influence on the other planets, including Earth. These gravitational influences, or tugs, occur due to the varying distances between the planets as they move in their respective orbits. Jupiter's orbit around the Sun takes approximately 12 Earth years to complete. As Jupiter and Earth move in their orbits, their relative positions change, leading to variations in the gravitational forces exerted by Jupiter on Earth. These tugs are more pronounced when Jupiter and Earth are aligned on the same side of the Sun or directly opposite each other. The gravitational pull of Jupiter during these alignments can cause small perturbations in Earth's orbit. While the Sun's gravitational pull on Earth is the dominant force governing Earth's orbit, Jupiter's gravitational influence, though much weaker due to the greater distance, can still cause measurable effects. These periodic tugs can induce small changes in Earth's orbit over long time scales. These small perturbations can, at least in theory, potentially lead to significant changes in Earth's orbit. However, the solar system is largely stable due to the balance of gravitational forces and the relatively stable configurations of the planetary orbits. This stability has been maintained over billions of years. This is what perplexed Sir Isaac Newton. He believed that the chaotic nature of the three-body problem, such as the interaction between Earth, Sun, and Jupiter, where two greater masses, the Sun and Jupiter, each exercise their control over a smaller mass, the Earth, would inevitably lead to catastrophic results. The world as we know it should have ended, and yet, here it was. Unable to come up with an explanation of the problem, the great scientist contended, as famous astrophysicist Neil deGrasse Tyson noted, that God simply willed this stability. However, Pierre-Simon Laplace was not content with this explanation. He studied these gravitational interactions and their potential impacts on the stability of the solar system and developed mathematical methods to analyze the stability of planetary orbits. Laplace extended Newton's work, developing mathematical techniques to solve complex systems involving multiple celestial bodies. His insights into perturbation theory, a method for analyzing how small disturbances affect the motion of celestial bodies, were particularly groundbreaking. Perturbation theory is a mathematical approach used to find an approximate solution to a problem by starting with a known solution to a simpler problem and adding small corrections. This method is particularly useful in celestial mechanics when dealing with the gravitational interactions between multiple bodies, such as the Earth, Sun, and Jupiter. In the context of the Earth-Sun-Jupiter system, perturbation theory helps us understand how the gravitational influence of Jupiter affects the orbits of Earth and other planets. First, we consider the simpler two-body problem, which is easier to solve. The primary interaction in this case is between the Earth and the Sun. According to Newton's law of universal gravitation, the gravitational force between Earth and the Sun determines the Earth's elliptical orbit around the Sun. When we introduce Jupiter into the system, we add a third body whose gravitational influence needs to be considered. The Earth-Sun system is now subject to additional forces due to Jupiter's gravity. These additional forces are the perturbations. To apply perturbation theory, we start with a known solution of the Earth-Sun two-body problem. This solution provides the baseline orbit of Earth around the Sun. We then add the gravitational influence of Jupiter as a small perturbation to this baseline orbit. The gravitational force from Jupiter causes slight changes in the Earth's orbital elements. As Jupiter moves along its orbit, its relative position to Earth and the Sun changes, causing periodic variations in the gravitational forces it exerts on Earth. These periodic forces induce corresponding periodic changes in Earth's orbit, known as periodic perturbations. Using perturbation theory, astronomers can calculate the effects of Jupiter's gravitational perturbations on Earth's orbit. These calculations involve solving differential equations that describe how the orbital elements of Earth change over time due to the perturbative forces. But that's not all. The theory also helps us assess the long-term stability of the solar system. By analyzing the cumulative effects of these perturbations over long periods, astronomers can determine whether the orbits of planets remain stable, or if they might undergo significant changes that could impact the overall configuration of the solar system. In summary, the complexities of the two-body and three-body problems reveal the delicate balance of forces that govern celestial mechanics. From the predictable orbits of the Earth-Moon system to the more chaotic interactions involving multiple celestial bodies, our understanding of these dynamics has profound implications for astronomy, space exploration, and our comprehension of the universe. The pioneering work of scientists like Newton and Laplace continues to inform and inspire contemporary research in the field, highlighting the enduring quest to unravel the mysteries of the cosmos. Astronomers have made several important discoveries about the behavior of planetary orbits over extended periods. For starters, the solar system is generally stable over long time scales and not chaotic as Newton had feared. This means that the planet's orbits do not change dramatically and remain in relatively predictable paths around the Sun, despite the gravitational influences from other planets, particularly massive ones like Jupiter. The overall configuration of the solar system remains stable. However, the planetary orbits do experience slow, long-term changes called secular perturbations. These changes include gradual variations in the shapes and orientations of the orbits. For example, the Earth's orbit slowly shifts over tens of thousands to millions of years, contributing to phenomena such as Milankovitch cycles that influence Earth's climate. These cycles are named after Serbian scientist Milutin Milankovitch, who proposed that variations in Earth's orbit and tilt cause climatic changes, including ice ages. Earth's orbit varies from nearly circular to more elliptical over a cycle of about 100,000 years. When the orbit is more elliptical, the difference between the closest approach and the farthest distance from the Sun is greater, affecting the distribution of solar energy received by Earth. Similarly, changes in the tilt affect the contrast between seasons. A higher tilt means higher contrast, while a lower tilt makes seasons milder. Another factor is precession, or the wobble in Earth's rotational axis, which changes the orientation of the axis over a cycle of about 26,000 years. This affects the timing of the seasons relative to Earth's position in its orbit. While the solar system is broadly stable, there are regions of chaos where small changes in initial conditions can lead to significant changes in orbits over long periods. This chaos is more pronounced in the outer solar system and in the asteroid belt, where gravitational interactions are more complex. Moreover, certain ratios of orbital periods can lead to resonances where gravitational influences are amplified. For example, Jupiter and Saturn are in a near 5:2 resonance, meaning that for every 5 orbits of Jupiter, Saturn completes roughly 2. These resonances can lead to significant gravitational interactions that affect the stability of orbits over time. Using perturbation theory, astronomers have been able to make long-term predictions about planetary motions. For instance, the accurate prediction of the positions of planets, moons, and other celestial bodies during spacecraft missions relies on perturbation calculations. The theory has also led to significant historical discoveries. The most famous example is the discovery of Neptune. Deviations in Uranus's orbit, which could not be explained by known planets, led to predictions of a new planet's existence, which was later discovered in 1846. The theory is also crucial in predicting the trajectories of asteroids and comets, allowing us to assess the potential impact risks of near-Earth objects by accurately modeling their orbits over time. So, were Newton's fears exaggerated or outright wrong? Not entirely. The three-body problem, in its complex form, involves determining the future trajectories of three-point masses given their initial positions and velocities. These calculations are based on Newton's laws of motion and his universal law of gravitation. Despite the foundational simplicity of Newton's equations, the three-body problem has no general closed-form solution. When three bodies interact gravitationally, their motions generate a dynamically chaotic system. This chaos arises because small variations in initial conditions can lead to vastly different trajectories over time, making precise long-term predictions impossible with a single equation. Instead, the behavior of such a system can only be accurately predicted by making calculations about the positions and velocities of the masses step by step. Historically, the first significant investigation of a three-body system involved the interactions between the Moon, Earth, and the Sun. This classic example highlighted the complexity and unpredictability inherent in gravitational interactions among multiple bodies. In a broader contemporary context, the term three-body problem can refer to any situation involving three interacting bodies, be they celestial masses or subatomic particles. Let's start with a simpler example of the three-body problem that is not as chaotic: double star systems. Also known as binary star systems, these scenarios are a common astronomical phenomenon where two stars are in orbit around their common center of mass. These systems vary widely in characteristics, including the distance between the stars, their mass ratio, and the orbital period. Let's take the example of the double star system as depicted in the fictional universe of Star Wars. In the film, the protagonist Luke Skywalker's home planet, Tatooine, a vast desert planet, orbits two suns, making it a circumbinary planet. While Tatooine is a fictional creation, circumbinary planets have been discovered in real-life astronomy. So, will such a system inevitably devolve into chaos? Well, not necessarily. The stability of a planet orbiting two stars relies on the delicate balance between gravitational forces. If the planet's orbit is sufficiently far from the binary stars, it can maintain a stable orbit for extended periods. In conclusion, the solar system's stability and the complex interactions between celestial bodies demonstrate the incredible balance of gravitational forces that govern their motions. While regions of chaos exist, and the three-body problem remains a challenge, our understanding of these dynamics continues to evolve. Advances in perturbation theory and observational astronomy have provided profound insights into the long-term behavior of planetary orbits, contributing to our knowledge of the universe and our ability to navigate and explore space. The gravitational pull exerted by each star creates stable regions where a planet can maintain a relatively stable orbit. These regions, known as Lagrange points, allow for stable orbits despite the presence of two gravitational sources. The stability of a circumbinary planet's orbit is influenced by factors such as the mass and orbital distance of the stars, as well as the planet's own mass and orbital characteristics. When these factors align favorably, a planet can orbit both stars in a stable manner, much like Tatooine in Star Wars. In this fictional example, the two stars or suns form a binary system. Tatooine's twin suns would orbit around a common center of mass based on their relative masses. If the stars were of equal mass, the center of mass would be midway between them, with each star following an elliptical or circular orbit around this center of mass. Tatooine would orbit this binary star system from a safe distance, in a manner similar to how Earth revolves around the single sun, making the orbit quite stable. This phenomenon is not purely fictional. For instance, Kepler-16b, a real exoplanet discovered by NASA's Kepler mission, orbits two stars in this way. The planet's stable path demonstrates how such a system can remain balanced, provided the planet is far enough away to experience a relatively uniform gravitational pull from both stars, ensuring the stability of its orbit. However, a three-sun system, also known as a trinary star system, presents a much more complex gravitational environment. Unlike binary star systems, trinary systems add another level of complexity due to the interactions between three massive bodies. Maintaining stable orbits within a three-sun system is inherently challenging due to the gravitational forces exerted by multiple stars. These interactions can lead to irregularities in the orbits of surrounding celestial bodies, including planets or smaller stars. The chaotic nature of three-body systems arises from the intricate interplay of gravitational forces. Unlike simpler two-body systems, where trajectories can be precisely calculated using Newtonian mechanics, three-body systems are notoriously difficult to predict. In a two-body system, such as the Earth and the Sun, their gravitational interaction is relatively straightforward, with each body orbiting around the other in a predictable pattern. However, when a third body, like another planet, is introduced, the gravitational pull of each body affects the other two. This situation is akin to trying to choreograph a dance with three partners who keep changing their steps unpredictably. This complexity makes three-body systems incredibly hard to predict accurately over long periods. Small changes in the initial positions or velocities of the bodies can lead to vastly different outcomes over time, much like predicting the weather months in advance, where minor changes now can lead to significant differences later. Generally, three-body problems are deemed unsolvable in most cases, as the orbits of the three bodies rarely stabilize, often resulting in dramatic outcomes. Gravitational forces can culminate in collisions between bodies or the ejection of one from the system, creating rogue planets drifting in space. Estimates suggest that rogue planets may outnumber stars in our galaxy. To address these challenges, scientists turn to computational simulations. Leveraging the power of computers, These simulations approximate the motions of celestial bodies in three-body systems, enabling predictions vital for space exploration. They are used for planning rocket trajectories and forecasting the fate of planets within multi-star systems. Science fiction also explores these chaotic dynamics, as seen in Netflix's adaptation of the three-body problem, featuring a planet trapped in a tumultuous orbit around three stars in the Alpha Centauri system. Such instability raises questions about the feasibility of life in such environments, a plot device in the series. Fortunately, Earth is not in such a chaotic situation, and while Newton's fears about chaos were justified, they do not pose an immediate threat to our existence. Laplace's work successfully predicted the nature of our orbit, and his meticulous calculations using perturbation theory allowed him to accurately predict the motions of celestial bodies, including Earth's orbit around the Sun. When Napoleon met Laplace and inquired why there was no mention of God in his work on celestial mechanics, Laplace famously replied, "I had no need of that hypothesis," suggesting that his mathematical explanations were so precise that they rendered divine intervention unnecessary. While Napoleon could breathe a sigh of relief as Earth faced no imminent cosmic threat, chaos is not entirely absent from our solar system. One potential scenario involves a significant asteroid impact. Although rare, such events have occurred in Earth's history and could disrupt the delicate balance of our solar system. A large asteroid collision could alter the orbits of planets, leading to chaotic interactions and potentially catastrophic consequences for life on Earth. Another possibility is the gradual weakening of the Sun's gravitational pull over time. As stars age, they undergo changes that can affect their gravitational influence on surrounding objects. While this process occurs over millions to billions of years, it could eventually lead to instability within the solar system. External factors, such as the gravitational influence of nearby stars or galactic interactions, could also perturb the orbits of planets in our solar system. While such events are less likely to occur in the near future, if they do happen, the resulting chaos could impact the long-term stability of our cosmic neighborhood. The story of chaos is not over yet. The unsolvable nature of the three-body problem continues to be a topic of study. For example, Jupiter, the largest planet in our solar system, exerts a profound gravitational pull on nearby celestial bodies. Over millennia, its gravitational interactions with other planets, asteroids, and comets have shaped the dynamics of the solar system. Despite its immense mass and influence, predicting Jupiter's precise effects over long timescales is exceedingly difficult due to the chaotic nature of its interactions. While Jupiter's gravitational influence helps maintain the stability of the inner solar system by deflecting potentially hazardous objects away from Earth's orbit, it can also destabilize the orbits of other bodies, leading to orbital resonances, collisions, or ejections from the solar system altogether. The intricacies of Jupiter's influence become even more apparent when considering its interactions with other gas giants like Saturn, Uranus, and Neptune. Despite the challenges posed by chaotic systems like Jupiter's gravitational influence, scientists continue to study and model these phenomena using advanced computational techniques. By simulating the dynamics of the solar system over extended time frames, researchers gain insights into the long-term evolution of planetary orbits and the stability of the solar system as a whole. However, the inherent unpredictability of chaotic systems underscores the limits of our ability to make precise long-term predictions in celestial mechanics. The challenges posed by chaotic systems extend to multi-body systems, including four-body and higher-order configurations. One significant area of study involves modeling star clusters, which exhibit complex and chaotic dynamics due to the gravitational interactions among multiple stars. In star clusters, numerous stars orbit each other under the influence of their mutual gravitational attraction. These systems can involve hundreds to thousands of stars, each exerting gravitational forces on one another. As a result, the collective behavior of stars within a cluster is inherently chaotic. Over time, gravitational interactions between stars can lead to phenomena such as stellar collisions, ejections from the cluster, or the formation of binary and multiple star systems. Modeling the evolution of star clusters requires sophisticated computational techniques that account for the complex interplay of gravitational forces among multiple bodies. Researchers use numerical simulations to track the trajectories of individual stars within a cluster over millions to billions of years, capturing the effects of gravitational encounters and dynamical processes on the cluster's evolution. Despite the inherent complexity and unpredictability of multibody systems like star clusters, studying their chaotic nature provides valuable insights into fundamental questions in astrophysics, including the formation and evolution of galaxies, the distribution of stars, and the dynamics of stellar encounters. While statistical models offer valuable insights into the behavior of complex systems, precise predictions remain elusive due to the inherent unpredictability of chaotic dynamics. Statistical modeling approaches aim to capture the probabilistic nature of chaotic systems by characterizing their behavior in terms of statistical distributions and patterns. These models provide valuable information about the likelihood of certain outcomes or the average behavior of a system over time. However, they often fall short of providing precise predictions for individual trajectories or specific events due to the sensitivity of chaotic systems to initial conditions. Understanding chaos in celestial mechanics is crucial for several reasons. First, chaotic dynamics play a significant role in shaping the evolution of celestial bodies and systems, influencing planetary orbits, asteroid dynamics, and the dynamics of star clusters. Moreover, chaos poses challenges for predicting the future behavior of celestial objects and systems, particularly over long timescales. The inherent unpredictability of chaotic systems underscores the limits of our ability to make precise predictions about the future evolution of complex systems in space. By combining theoretical insights with computational techniques, researchers can uncover patterns in chaotic systems, identify underlying mechanisms driving their behavior, and develop statistical models that capture their essential features. While precise prediction may remain elusive for chaotic systems, the quest to understand and characterize their dynamics continues to drive advancements in our understanding of the universe.